Everyone uses large language models. Almost nobody can say what happens between your prompt and the answer. There is no magic here and no thinking in the human sense. It is a stack of math you can actually understand. Over the next 10 minutes, we go from raw text to a working model one layer at a time. It all starts with tokens. A model never actually sees letters or whole words. A tokenizer first chops your text into chunks called tokens. Common words become a single token. Rarer ones split apart, so tokenization might become token and ization, two pieces. Even spaces and punctuations actually count. This is why a model struggles to spell or count letters. Ask how many R's are in strawberry, and it often misses for sure because it never sees STRAWBRRY as in like normal letters. It sees three tokens with no letters inside. Every token maps to an integer ID, and that list of integers is all the model ever receives. Two practical effects are actually follows because of this. You pay per token, not per word, and your context limit is measured in tokens too. So hopefully that explains why tokens are actually much more important in terms of like how your LLM actually works. Now let's move on to the second step, which is embeddings. So embedding is also an interesting characteristics when it comes to LLM. So like let's say integers alone carry no meaning. So each token ID is turned into a vector basically. So a long list of numbers through a lookup table called an embedding. Picture every token as a point in space with thousands of dimensions. The trick is that meaning becomes geometry. Words used in similar ways end up near each other. King sits close to queen. Paris relates to France the way Tokyo relates to Japan. You can even do arithmetic ones. Take the vector for king, subtract men, add woman, and you land near queen. These vectors are not hand coded, by the way. The model actually learns them from data, nudging each one until the geometry matches how words actually get used. From here on, the model works entirely within these vectors, so there is no other scenario like actual words in it. It's always within these vectors. And the next step would be attention. So now the core idea that made modern morals possible is because of attention. Read this sentence. The cat sat because it was tired. You know it refers to the cat, not the floor. Because like as from human being perspective, we know that it obviously means cat over here. The model figures this out with attention. For every token it builds three vectors, a query, a key, and a value. The query is what this token is looking for. The key is what each token offers. The model compares the query of it against the key of every other token. Cat matches best, so it pays most of its attention there and pulls in cat's value. Do this for every token at once, and each word updates itself based on the words that matter to it. Stack this many times, and the model builds a context aware understanding of the whole sequence. That's how the whole attention layer works. And then comes transformer. Attention is the heart of the transformer, the architecture behind almost every modern model. So a transformer is just attention layers and ordinary feed forward layers, stacked and repeated, sometimes dozens of times. So there is one more problem to solve. Attention treats token as a bag with no sense of order. But dog bites man and man bites dogs are very different. So the model adds positional information to each token, encoding where it sits in the sequence. So modern models use a method called rope that rotates each vector by an angle based on its position. So the model reads the distance between words, which means that like in tokens in vectors out, and then attention and feed forward layers in between. That is the whole shape of how a transformer works. So one obvious question in this after you learned all of this, like you're thinking like, okay, how does the model learn all of this? So basically it's one task repeated trillions of times. It's the whole purpose of the model is that predict the next token. Feed it a sentence with the last word hidden, it guesses. Compare the guess to the real word, measure the error, and adjust every weight a tiny amount to be a little less wrong. So this is the whole purpose of this model, how it's being trained. That adjustment is what you call backpropagation and gradient descent. Do this across much of the public internet, and the model is forced to learn grammar facts, reasoning patterns, and style, all just to predict the text better. After that comes fine tuning, where humans rate answers and the model is shaped to be helpful and safe. But underneath it, it's still one thing, a very good next token predictor. So now you have the model within your hands basically. So when you use the model, what is that step is called? It's called inference. So basically what it's doing is that it produces a probability for every possible next token, then picks one, adds it, and repeats the whole process again. So how it picks is up to us basically. So temperature controls randomness. So low temperature sharpness sharpens the odds. So the top token almost always wins and answers stay focused. High temperature flattens them. So less likely tokens get a turn and the output gets more varied. So two more knobs narrow the field first, which is top K keeps only the K most likely tokens, and then top P keeps the smallest set that adds up to a probability you choose. So tuning these in how you move between precise and exploratory answers. So none of this is creativity, it is controlled sampling from a distribution. Okay, so once you have done this inference and sampling, basically you control these parameters, right? So after that, the whole limitation that happens, what you build is like these are the two limits which shapes everything you build. The context window is how many tokens the model can hold at once, your prompt plus all its replies, even the history ones as well. So go over it and the oldest tokens just falls away and cost grows fast. In attention, every token looks at every other token. So doubling the input does not double the work, it roughly quadruples it. That is why long prompts get expensive quickly. The fix in practice is to send less, trim the prompt, summarize history, and cache the parts that repeat. Most real world LLM cost is a context management problem, to be honest. So let's say you tackle all of this, but the issue is that you have your own data, and then the model, a raw model, only knows what it saw in training, and it cannot take actions as well. So we can actually add more things on top of it. So like we have three techniques which will fix most of our issues. The first one is retrieval, often called RAG. You store your documents as vectors, find the chunks closest to a question, and paste them into the prompt so the model answers from your data without retraining. Second one is tools. You describe a function as a schema and the model can ask to call it, returning JSON with the name and arguments. Your code runs the real action and hands back the results again within a JSON format. Third, agents. Wrap all of this in a loop. The model picks an action, your code runs it, the result goes back in, and it repeats until the task is done. So an agent is mostly a while loop around a model, some tools and some memory associated with it. So we have all of this, the tools, the agents, and the model itself. But like most of the time, the people ask me questions like, okay, you would need a data center to run one of these, right? But to be honest, we don't need a data center to run a model locally. Like you can run it locally, basically. That's what I'm trying to say. So there are tools like Olama run open models on your own machine with a single command. The model ships as one single file within often in GGUF format, holding the weights, the tokenizer, and the metadata all together. The catch is memory. Full precision is very heavy, so weights are most of the time quantized, stored in fewer bits. A name like Q4 means 4 bits per weight, cutting the file roughly 4 times with a small quality cost. That is how a model with billions of parameters fits on a laptop. Smaller models run on a CPU, larger ones want a GPU or Apple's unified memory. You can even have multiple GPUs clustered together, but that's also another scenario which you can tackle. So to recap, this is it. This is end to end. Text becomes tokens, tokens become vectors, attention mixes them by context, transformer layers repeat that, train to predict the next token. At inference, you sample from its predictions inside a context window that actually costs you. And with retrieval tools and a loop, a predictor becomes something that can act. No magic, just layers of math. And now you can see all of them. If you have any questions, let me know in the comments.